Hello. This will be a demonstration of proposition 13 from book 8 of Euclid's Elements, which says that if numbers be in continued proportion, their squares will also be in continued proportion, and likewise their cubes too will be in continued proportion. We're given, right off the bat, a continued proportion made up of three numbers. So A, B, and C, they form a continued proportion, so that A is to B just as B is to C. Furthermore, we're also given their squares and cubes. So A squared makes a D, B squared makes E, and C squared makes F. And again, A cubed makes G, B cubed makes H, and C cubed makes K. And what we want to prove about these squares and cubes is that they form another set of continued proportions. So that D is to E just as E is to F, and furthermore that G is to H just as H is to K. We're going to begin proving this by creating some numbers, first among which is the number L. The number L will be the product of A and B. So A times B makes L. What we're going to do next is we're going to take this number L and multiply it by those two numbers again. We're going to take the product of A and L and the product of B and L. A times L is going to make M, and B times L will make N. We're going to do a similar thing with B and C. We're going to take their product, B times C, that's going to make the number O. And we're going to take this number O and multiply it by B and C again, so that B times O makes P, and C times O makes Q. Now, similar to the preceding propositions, namely propositions 8.11 and 8.12, but you can trace this sort of reasoning all the way back to proposition 8.2, that the three numbers D, L, and E form a continued proportion in the same ratio as A to B, and likewise, the numbers G, M, N, and H form another continued proportion also in the same ratio as A to B. We also know two other continued proportions in the same ratio as B to C, namely E, O, and F. Those three numbers will make another continued proportion, but this one will be in the same ratio as B to C. And again, we know the four numbers H, P, Q, and K form yet another continued proportion, this one in the same ratio as B to C as well. Now, Euclid doesn't go through how exactly we get to all of these continued proportions and how they're all the same with our given ratios. He does this because we've seen this sort of logic play itself out in multiple propositions before this. We can trace this all the way back to 8.2, but most recently we've seen this in 8.11 and 8.12. What exactly does that logic consist in? It consists in a ton of uses of proposition 7.17. You can go back to those propositions 8.2, 8.11, and 8.12 to see how this plays out explicitly, because Euclid doesn't do it explicitly. I won't do most of it explicitly either, but I will go through this first example about the three numbers D, L, and E, just for the sake of clarity and to sort of, help guide you into realizing where the rest of this step comes from. So, we know that the number A times the number A makes D, and we know that the number A times the number B makes the number L. So we have one number A multiplied by two numbers A and B to make two products, D and L. And we know by proposition 7.17 that those two numbers will have the same ratio as the products so produced, so that A is to B just as D is to L. We can go through similar reasoning to show that A is to B just as L is to E, because B times A makes L, and B times B makes E. And again, we know from 7.17 that those two numbers multiplied will have the same ratio as the product so produced, so that A is to B just as L is to E. But we had just proven that A is to B just as D is to L, so we have two ratios which are the same with the same ratio. Property of numbers tells us that they are in the same ratio with one another, so that D is to L just as L is to E. Or in other words, those three numbers D, L, and E form a continued proportion, all in the same ratio as A to B. You can go through similar reasoning to get the continued proportion G, M, N, and H to be in the same ratio as A to B. And the other two continued proportions will follow similar steps, but using the ratio B to C instead of A to B. That out of the way, We then remember our given. Our given was that A, B, and C form a continued proportion, or in other words, that A is to B just as B is to C. So what our next move is going to be is to take our continued proportions and put them in equality with one another. So remember that D, L, and E form a continued proportion in the same ratio as A to B. E, O, and F form a continued proportion in the same ratio as B to C. But we know that A is to B just as B is to C. Those two ratios, A to B and B to C, are just the same ratio. And so we have two continued proportions in the same ratio with equivalent ratios. So property of numbers tells us that they are the same with one another, so that D, L, and E is a continued proportion in the same ratio as E, O, and F. And we can take similar steps to put the four-term continued proportions in equality with one another, so that the continued proportion G, M, N, and H is in the same ratio as H, P, Q, and K. Next, let's focus on the three-term continued proportions of D, L, E, E, O, and F. Now, we know that D is to L just as E is to O. How we know this is that D is to L just as A is to B. E is to O just as B is to C, but we know A is to B just as B is to C, so we have two ratios which are the same with equivalent ratios. Property of numbers tells us they are the same with one another, so that D is to L just as E is to O. You can go through similar reasoning to arrive at the fact that L is to E just as O is to F. So what we have right here is the perfect setup for proposition 714, that xi quality, D is to E just as E is to F. So skipping over the middle terms of L and O to compare the extremes D and E and F directly to one another. Again, that's proposition 714. So that D is to E just as E is to F. But that is equivalent to saying that D, E, and F form a continued proportion, because D is to E just as E is to F. So that proves that D, E, and E form a continued proportion, which is part of what we wanted to prove. And we can go through similar reasoning to get us to the fact that G is to H just as H is to K, again by comparing the four-term continued proportions of G, M, N, and H, and then H, P, Q, and K, using proposition 714 to compare their extremes directly to one another, so that G is to H just as H is to K. And again, that's equivalent to saying that G, H, and K form a continued proportion. And this is what we wanted to prove. We wanted to prove that D, E, and F form a continued proportion, and that G, H, and K form yet another continued proportion. And we just done that, so we're done with the proposition, therefore, etc., Q, E, D. Again, you know me, I always like to give particular numerical examples after every proposition, so let's do that right here. 4, 6, and 9, these three numbers form a continued proportion. I've used that multiple times by now. It's just very nice. I like it. It's all in a 2 to 3 ratio. I don't have to deal with any 1 to 2s or 1 to 3s. It's nice. I like 4. I like 4, 6, and 9. So we have three numbers which are in a continued proportion. What this proposition allows us to say is that if we square all three of these numbers, those squares will be in yet another continued proportion. So let's play that out. 4 squared is 16. 6 squared is 36. And 9 squared is 81. Now these three numbers, 16, 36, and 81, form a continued proportion, because we recognize that 16 is to 36, just as 36 is to 81. Namely that these are actually in 4 to 9 ratios, because we can divide a 4 out of 16 and 36 to reduce it to 4 to 9, and we can divide a 9 out of 36 and 81 to reduce that to a 4 to 9 ratio. We can do this sort of process again, but instead of squaring, we're going to cube these numbers, and this proposition also tells us that those numbers will be in continued proportion with one another. 4 cubed is 64, 6 cubed is 216, and 9 cubed is 729. Now, you can do some math. These three numbers, 16, 26, and 729, these form yet another continued proportion, because 64 is to 216, just as 216 is to 729. The math you have to do to realize this is that if you take the ratio 64 to 26, you divide out all their common factors, you get a 16 to 81 ratio. And you can do the same thing for 216 and 721. You can simplify that into a 16 to 81 ratio as well to recognize that these two numbers, 64 to 216 and 216 720, those are equivalent ratios. So those three numbers make a continued proportion. You can actually extend this to any arbitrary power. So if you have, so we could take 4 to just any power n, 6 to any power n, and 9 to any power n will form a continued proportion. Euclid just deals with where n is 2 and 3, as we would say nowadays, the square and cube cases, but you can easily take this into where n equals 4, or n equals 5, or n equals 100. You can use the same sort of logic to prove that 4 to the n, 6 to the n, and 9 to the n will always form a continued proportion. Now, I don't want to end the video there because I do want to say a little bit more about that second step there. We've seen this sort of, actually not just the second step, the first and second step. We've seen this sort of construction of numbers and this sort of logic using 717 to prove continued proportions. What I want to do is I want to generalize in a way that Euclid doesn't. What I want to do is I want to just run you through very quickly how exactly you get continued proportions and how to prove that they're in continued proportions. And to do that, I will just take any two numbers, A and B. So A and B, those can be any numbers. What I want to do is I want to create continued proportions in the same ratio as A to B. So say I want a 3-term continued proportion. What I'm going to do is I'm going to square A. Next, I'm going to take the product of A and B. And finally, I'm going to take the square on B. This does form a continued proportion in the same ratio as A to B. Because if you take A squared over AB like that, you can just divide out a common A to get A to B. And like that, that's our given ratio. And you can do the same thing between AB and B squared. They have a common B, so you can divide that out, and you're left with A divided by B, which was our given ratio. How exactly we see that play out here is in the continued proportion of D, L, and E. Because we know D is A squared, L is A times B, and E is B squared. So you see how this sort of thing plays out. But what if I don't want a 3-term continued proportion? I instead want 4 numbers in continued proportion in the same ratio as A to B. Well, what I'm going to do for that is I'm going to take the cube on A. Next, I'm going to take the square on A and multiply it by B. The next step will be to take A and multiply it by the square on B this time. And the last step, of course, is to take the cube on B. I am sort of just rehashing proposition 8.2, but I'm doing that for an important reason. I want to generalize this sort of process and play out the logic for you in clear and generalized terms. So this is how you would make a continued proportion whose terms are in the same ratio as A to B. You can recognize this because if we have A cubed, divide that by A squared over B. Well, both of these have 2 A's. So we can take those 2 A's out, and we're just left with A and B. Of course, A cubed, you take out A squared, you're just left with a single A, and A squared B, you take out the A squared, you're just left with B. So again, we have our ratio A to B, which was our given ratio. And you can continue doing this for all the terms A squared B, AB squared, and B cubed. But what if I don't want a 4-term continued proportion? I want 5-term continued proportion, or I want 6, or I want 100. Just if I want any number of numbers in continued proportion in a given ratio, how would I make that? Some of you may have already realized the sort of pattern that plays itself out here, but this does take, you got to be sharp with these sorts of things. I certainly wasn't for a long time. It took me a little while to realize the pattern here, so I'm going to walk through it. If you want any number of numbers in continued proportion, say you want 5 numbers or 6 or 7, just n numbers, just any number of numbers in continued proportion. How you're going to pull that off is you're going to take a and raise it to the power of n. N here is the number of numbers we want in continued proportion. The next step will be to take a n minus 1 b. The next step will then be to a n minus 2 b squared. And you continue this until you reach a squared b n minus 2, a b n minus 1. Your final term will be b to the n. This is generally how you make a continued proportion in any number of terms. And you can see this play out in Euclid whenever he goes through all of this multiplication and he goes through proposition 717, all of this. He's doing this. This is how we would express this in sort of modern algebraic terms. I hope that helps. It at least helps me to see the general pattern here. And it makes steps where he just says, similar to the preceding, if you know the general formula of how he gets this stuff, then this really doesn't bother you. It didn't bother me after I realized these formulas. So I hope that this formula being shown to you, it helps you get through these propositions when they do pull this sort of stuff and expect you to remember how exactly we get continued proportions. This is how we get them. That's all I've got to say about this one. I hope it was helpful. If it wasn't, comment section is always open. So with that said, I'll end the video here and move on to proposition 8.14.